Hello everyone, I am Navyashree. I am studying my Masters in Computer Science at Manasa Gangotri, Mysore. My seminar topic is Ensemble Learning, Bagging and Boosting. So let us discuss about Ensemble Learning, Bagging and Boosting in Machine Learning. The content is Ensemble Learning, Bagging and Boosting. So, firstly, what is ensembling? Ensemble methods is a machine learning technique that combines several base models in order to produce one optimal predictive model. To better understand this definition, let's take a step back into ultimate goal of machine learning and model building. Hello everyone, I am Navyashree. I am studying my Masters in Computer Science at Manasa Gangotri, Mysore. My seminar topic is Ensemble Learning, Bagging and Boosting. So let us discuss about Ensemble Learning, Bagging and Boosting in machine learning. The content is Ensemble Learning, Bagging and Boosting. Next is bagging. In parallel methods, we fit the different considered learners independently from each other's and so it is possible to train them concurrently. The most famous such approach is bagging, that aims at producing an ensemble model that is more robust than the individual models composing it. In bagging, random forest is an example. The random forest approach is a bagging method where deep trees fitted on bootstrap samples are combined to produce an output with lower variance. However, random forests also use another trick to make the multiple fitted trees a bit less correlated with each others. When growing each tree, instead of only sampling over the observation in the data set to generate a bootstrap sample, we also sample over features and keep only a random subset of them to build the tree. Sampling over features as indeed the effect that all trees do not look at the exact same information to make their decision, and so it reduces correlation between the different returned outputs. Another advantages of sampling over the feature that it makes the decision making process more robust to missing data. Observation with missing data can still be regressed or classified based on the trees that take into account only features where data are not missing. This random forest algorithm combines the concept of bagging and random feature subspace selection to create more robust models. So, it is random forest method. It is a bagging method with trees as weak learners. Each tree is fitted on a bootstrap sample, considering only a subset of variables randomly chosen. So that is the diagram of random forest. Next is boosting. In sequential methods, the different combined weak models are no longer fitted independently from each other. The idea is to fit models iteratively such that the training of model at a given step depends on the models fitted at the previous steps. Boosting is the most famous of these approaches and it produces an ensemble model that is in general less biased than the weak learners that compose it. So adaptive boosting is an example of boosting. In adaptive boosting, we try to define our ensemble models as a weighted sum of L weak learner. Finding the best ensemble model with this form is a difficult optimization problem. Then, instead of trying to solve it in one single shot, means finding all the coefficients and weak learners that give the best overall adaptive model, we make use of iterative optimization process that is much more tractable, even if it can lead to a suboptimal solution. More especially, we add the weak learners one by one, looking at each iteration for the best possible pair, coefficient weak learners, to add to the current ensemble model. In other words, we define recurrently the S slash N such that where C underscore L and W underscore L are chosen such that S underscore L is the model that fit the best the training data, and so that is the best possible improvement over s underscore of 1 minus l. We can then denote this is the formula. So where e is the fitting error of the given model and small e is the loss or error function. Thus, instead of optimizing globally over all the L models in the sum, we approximate the optimum by optimizing locally, building and adding the weak learners to the strong models one by one. More especially when considering a binary classification, we can show that the AdaptBoost algorithm can be rewritten into a process that proceeds as follows. First, it updates the observation weights in the dataset and train a new weak learner with a special focus given to the observation misclassified by the current ensemble model. Second, it adds the weak learner to the weighted sum according to an update coefficient that express the performance of this weak model. The better a weak learner performs, that more it contributes to the strong learner. So, assume that we are facing a binary classification problem with n observation in our data set, and we want to use AdaBoost algorithm with the given family of a weak models. At the very beginning of the algorithm, all the observation of the same weights 1 by n. Then we repeat L times for the L learners in the sequence as the following steps. So, fit the best possible weak model with the current observation weights. Second is compute the value of the update coefficient, that is some kind of scalar evaluation metric of the weak learner that indicates how much this weak learner should be taken into account into the ensemble model. Third one is update the strong learner by adding the new weak learner multiplied by its update coefficient. Fourth is compute new observation weights that express which observation we would like to focus on the next iteration. So weights of the observation wrongly predicted by the aggregated model increases, the weights of the currently predicted observation decreases. Fifth is repeating these steps. We have then built sequentially our L models and aggregate them into a simple linear combination weighted by coefficients expressing the performance of each learner. Notice that there exist variants of the initial AdaBoost algorithm such that logit boost classification, L2 boost regression, that mainly differ by their choice of loss function. So this is the AdaBoost updates weights of the observation at each iteration. Weights of well classified observation decreases relatively weights of misclassified observation. Models that perform better have higher weights in the final ensemble model. This is the adaptive boosting. Thank you.